In this video, we're going to look at the best approximation theorem, which states the following. Let W be a subspace of Rn. For any vector y in Rn, let y hat be the projection of y onto W. Then y hat is the closest point in W to the vector y, in the sense that if I look at the distance between y and y hat, that's going to be less than the distance between y and the vector v for all vectors v in W distinct from y hat. So let's start by drawing a picture. Suppose that I have the origin here, and suppose that this is my subspace W. Now suppose that I have a vector y like this. Now let's decompose y into a part that's in W and a part that's in W perp. The component in W we label as y hat. The component in W perp we usually label as z, but in this theorem we're just going to keep it as y minus y hat. Now let's draw any other vector that's in W. We'll call it v. Now the vector y minus v would be this vector. So what we want to show is that y minus y hat has a shorter length than y minus v. So let's begin our proof. Let v be any vector in W that's distinct from y hat, which is the projection of y onto W. Consider the vector y hat minus v. In our picture, it would be this green vector. Since y hat is in W and v is in W, their difference must also be in W. And since y minus y hat is in W perp, I know that y minus y hat and y hat minus v are orthogonal. So in my picture, I have a right angle right here. So the vectors y hat minus v, y minus y hat, and y minus v form a right triangle. Using the Pythagorean theorem, we have that the length of y hat minus v squared plus the length of y minus y hat squared is equal to the length of y minus v squared. Since the vector v is distinct from y hat, I know that y hat minus v is not the zero vector, which means it has length greater than 0. Therefore, we can conclude that the length of y minus y hat squared is less than the length of y minus v squared. And finally, taking the square root of both sides, we have that the length of y minus y hat is less than the length of y minus v. And that concludes the proof of the theorem. So again, this theorem tells us that the projection of y onto W is the vector in W that's closest to the vector y. So sometimes this projection is called the best approximation to y by elements of W. Let's look at an example of how we would apply this theorem. So in this example, u1 is the vector 1, 2, 1, and u2 is the vector 1, negative 1, 1. Let W be the plane spanned by u1 and u2. Let y be the vector 6, 1, 4. We want to answer two questions. What is the closest point on the plane to y, and what is the distance between the plane and y? So according to the best approximation theorem, if I want to find the point on the plane closest to y, I need to take the projection of y onto W. And if I want to take the projection, I need to make sure that u1 and u2 form an orthogonal basis for W. So we need to check whether u1 and u2 are orthogonal. So let's take the dot product of u1 and u2. This gives me 1 times 1 plus 2 times negative 1 plus 1 times 1, which is 1 minus 2 plus 1, which is 0. So u1 and u2 are orthogonal. And if they're orthogonal, we know that they're linearly independent. And so since they're orthogonal, linearly independent, and they span W, we know that u1 and u2 form an orthogonal basis for W. So now we can use the projection formula. Y hat is equal to y dot u1 divided by u1 dot u1 times the vector u1 plus y dot u2 divided by u2 dot u2 times the vector u2. So we have y dot u1, which is 6 times 1 plus 1 times 2 plus 4 times 1 divided by u1 dot u1, which is 1 squared plus 2 squared plus 1 squared times u1, which is 1, 2, 1. I want to add this to y dot u2, which is 6 times 1 plus 1 times negative 1 plus 4 times 1 divided by u2 dot u2, which is 1 squared plus negative 1 squared plus 1 squared, times u2, which is the vector 1, negative 1, 1. Simplifying this, we get 12 over 6 times 1, 2, 1 plus 9 over 3 times 1, negative 1, 1. So we have the vector 2, 4, 2 plus the vector 3, negative 3, 3, and that sum is 5, 1, 5. So the point on the plane that's closest to y is the point 5, 1, 5. If I want to find the distance between the plane and y, I would need to find the orthogonal component. So I need to find z, which is y minus y hat, then take the length of z. So in this case, z is the vector 6, 1, 4 minus 5, 1, 5, which gives me 1, 0, negative 1. The length of z would then be the square root of 1 squared plus 0 squared plus negative 1 squared, or square root of 2. And that's the distance between the plane and y. So that's where we'll stop for this video. One important thing to note is that when we take these projections, we need an orthogonal basis. So what if you don't have an orthogonal basis? In the next videos, we'll talk about something called the Gram-Schmidt process, which is a way to turn a regular basis into an orthogonal basis.